Okay, we're going to take a look at exercise 21 out of chapter 4, section 2. And we're asked to show that these functions have exactly 1, 0 on the given interval. Well, first, to establish that they have a 0 on an interval, we can use the intermediate value theorem that states if we have a continuous function on a closed interval and we see a change of signs between the endpoints, that it has to cross 0. Well, all polynomials are continuous, so if we go ahead and evaluate the function at -2 and evaluate the function at -1, if we see our change of sign, we have the existence of at least 1, 0. So that will give us a nice start to this here. So -2 to the 4th power is 16. -2 times 3, that's going to become a -6. Plus 1, that's going to be 11. So we have a positive value. And for f of -1, -1 to the 4th power is 1. Plus 3 times -1 is -3 plus 1. That is -1. So by the intermediate value theorem, there has to be at least 1, 0 between -2 and -1. But our instructions are to show that there is exactly 1, 0 between it. So the next thing we should do is probably take the derivative of this function. Because if we could show that this function is, in this case, strictly decreasing, because it's, if we were to graph this out, f of -2 is 11, f of -1 is -1. So if we could show that this function's strictly decreasing, then we can guarantee that there's exactly 1, 0 between -2 and -1. So the derivative of our function is (4x cubed plus 3). Now, typically right here, I'd go for running a sign chart on the variable. And if we show that it's negative in the region that covers -2 to -1, we would be good to go. This one calls for us to do something a little bit different. And what we do know is that we're only looking at this derivative where x is on the open interval from -2 to -1. And I'm writing the open interval as an inequality here. And what I'm about to do works because we've only got one term with a variable here. So if this doesn't seem immediately intuitive to you, it didn't pop into my head the first time I took a quick look at this either, so don't feel bad at all. But if we were to go ahead and we're going to take this x here and we're going to try to build the derivative in here. And if we see that our endpoints remained negative, then we have shown that the derivative is going to be negative on this open interval. So what we're going to do here is we're going to go ahead and we're going to cube everybody. And that doesn't alter the inequality. So that's a legal move there. Because you got to be careful when you're working with inequalities. There's some things that you will do that may not preserve the inequality. Raising to an odd power preserves the inequality. So that was good. Next thing that we're going to do here is we're going to multiply everything through by 4. So we get negative 32 less than 4x cubed less than negative 4. And then now we're going to go ahead and add 3 to everybody. And that gives us negative 29 less than 4x cubed plus 3 less than negative 1. And that means that our derivative on this interval is less than 0. So on this open interval, it's a strictly decreasing function. We were able to go ahead and show that this has to be the case.